Hi everyone. Today we are going to discuss about the data synthesis. So basically we are going to talk about the pooling of data, that is meta-analysis. So preparation for the synthesis of data should be started very early. It should be started at the protocol stage, when you are writing the protocol, when you are registering the protocol in the Prospero or some other websites. In the protocol itself, we normally mentions what we are comparing. Whether we are comparing drugs with the placebo or control or standard care, or one drug with another drug. So that should be mentioned in the protocol stage, in the protocol itself. And when we collect all the studies which we are going to include in the meta-analysis, and when we prepare the study characteristics table during the meta-analysis, at that time also we get a fair idea about the type of studies which are similar enough to be grouped together, and we can get a fair idea about what type of data, what type of outcome data is available, and in how many studies that particular outcome data is available. So based on that, and based on the similarity of studies, we get a good idea that what type of and how many studies we can pool together for that particular outcome. Sometimes we may require some modification in the planned comparison, or we may require some modification in the type of outcomes. We may need to have some particular type of subgroup, or we may need to find or fine-tune some particular outcome. In that case, we need to go back to the protocol and we can request for the modification of protocol. So basic idea is the meta-analysis component need to be planned much early before actual data analysis in the software. So this is a simplistic view. When we have similar studies and similar outcomes, then meta-analysis is possible. When we have very different studies and different outcomes, the meta-analysis is not possible. So if you want to see the effect of one drug in comparison with the placebo on systolic blood pressure, and if we have all the studies, if we include the studies which has systolic blood pressure, and the studies are similar, means all the studies have adult patients, and it has the drug which is of interest to us. It has control, which is the part of our PICO, and when it has that particular outcome, that is systolic blood pressure, then meta-analysis is possible. But if there are two studies, one has systolic blood pressure and one has ambulatory systolic blood pressure, then we cannot pool the data together. We can pool the data only for the ambulatory blood pressures and office blood pressure separately. In case when there are different studies or different outcomes, we may choose some other methods of data synthesis. It may be a qualitative synthesis, where we just list the type of studies and describe these studies in some detail, or there may be some other methods which we can use. But in that case, the quantitative synthesis, the meta-analysis is not possible. So here you can see a typical forest plot which looks very difficult to make, but software make it very easy. So people should not get afraid of meta-analysis looking at the forest plot, because it can very easily be prepared by the software. So a typical meta-analysis has the following components. It has summary statistics calculated for each study. So here you can see that each study has different summary statistics. So one component of a meta-analysis is that we have the result in the form of summary statistic of each studies. Another component is we have a combined average of the summary statistic. So based on different results from the different studies, a average, or rather a weighted average of the effect is calculated, based on which the conclusion is made. So we have the summary statistic as a weighted average of the intervention effect of all the studies included in the meta-analysis. This is the second component which is there in the meta-analysis. Then we have to assume whether we are going to use fixed model or a random effects model. So fixed effect or random effects. So looking at the, here you can see they have used fixed effect model, but we can use the random effect model also based on our assumption. Now what are those assumptions? So here we can see that in fixed effect, it is assumed that each study has the same effect size. The magnitude of effect in the each study is same. Whatever difference is there in each study, that is because of the sampling error, that is because of the chance. That is the assumption for the fixed effect model. While in the random effect model, it is assumed that each study has a effect size which is not fixed. The effect size or magnitude of effect of these studies are distributed in a pattern which is normally a normal distribution, and any difference of the effect size between the studies not only because of the random error or sampling error, but also because of the true effect of the intervention. So in the fixed effect, it is assumed that the effect is same in each study, while the random effect, the effect is similar amongst the different studies, but it follows a normal distribution. Now looking at the assumptions, we can say that using fixed effect may not be a good idea, because it is very difficult to assume that the intervention will have same effect in different kind of studies. It may be similar effect, but it will have some distribution based on the type of people, based on the geographical location, based on some other parameters. So this is also very important component of the meta-analysis, fixed effect versus random effects. And then we have the summary statistics based on the standard error. So based on the standard error, we calculated the confidence interval around a resultant effect, around a combined intervention. And this confidence interval, so this is the weighted summary statistic, which is a combination of all these summary statistics. And then this is a confidence interval, which is calculated based on the standard error, and this shows the certain uncertainty about this result. So uncertainty also measures the precision, and it is also helpful in finding the p-value. So the standard error of the summary of intervention effect is useful in calculation of the confidence interval, which shows the precision or uncertainty, as well as the p-value, which if significant shows that results are significant. Now another very important component is heterogeneity. So what heterogeneity shows? Heterogeneity shows the variation in the effect size of amongst the studies, which is more than the variation which can be explained by the random error. So if we consider random error, if we consider random effect, sorry, I want to repeat here, that this heterogeneity shows the variation amongst the effect size in different studies, which is more than which can be explained by the random effect model. So in the random effect model, we have assumption that these effect size are normally distributed, but if the deviation is more than this, then there is something with the studies which is making it very much different from other studies. So there are some statistics which measures the heterogeneity. One is chi-square value, which you can see here. This is the p-value of chi-square value, and another is I-square value. So this is very important part of the meta-analysis, the calculation of heterogeneity. Next screen shows what kind of summary statistic we can use for the dichotomous data. From here we can select whether we want to use fixed effect model or random effect model. You all know that fixed effect and random effects, how to choose, that we are going to discuss in bit detail in coming slides. But at least you know that we have to choose one out of these two, and then we can choose odds ratio, risk ratio, risk difference, and there is one more, that is number needed to treat or number needed to harm. So out of these four, we can choose any. Now when we click next, we get this box here. So this is the first clinical trial or a study. Now here we can add the event. So in the case of, so now we are describing dichotomous data. We can add event here, total sample size, event in control, total sample size, and we will get odds ratio, or we can change odds ratio to risk ratio by clicking on this button. We can add more studies by clicking on this button. So here you can see we have included one more study, and I have included the data, some data where events are mentioned here, 3 out of 50. It may be anything, it can be a harmful event or beneficial event. In the control it is 20 out of 60. In another trial the event is 2 out of 50, in control it is 7 out of 50. And here you can see the odds ratios, and you can see the resultant effect. This is the confidence interval. So this is how we add the data dichotomous data, and this is how we do the meta-analysis. So we can change the odds ratio to risk ratio from here. We can change the fixed effect random effect model from here. If you click here, it will give us the picture of forest plot, which you can observe here. From here you can enter the study. This simple thing, and you can very easily learn from in the Raven. So if you look at the different type of dichotomous outcomes, there are some relative measures and there are some absolute measures. The relative measures, we have risk ratio, also known as relative risk or odds ratio. In absolute measures, we have risk difference or absolute risk reduction, and number needed to treat and number needed to harm. Now, out of these four, there are different parameters based on which we should select one. Now, if we go through the Cochrane Handbook for System Reviews, they have given details account of how to select one out of these four. So there are three main criteria, which is consistency, mathematical properties, and ease of interpretation. And based on these criteria, I don't want to go into detail because of the brevity of time. Based on all these criteria, we should prefer risk ratio or odds ratio, and my favorite is risk ratio because risk ratio is easy to interpret, while odds ratio may not be as easy to interpret for the clinician. Ultimately, our result should be meaningful to the end users. So in that context, risk ratio is better as compared to odds ratio. If you want to interpret and it results in the odds ratio, then you can convert it into risk ratio to make it more. Now, what to do when there is a zero event in one group? In that case, it will be difficult to calculate risk ratio or odds ratio. So, instead of 0, we can add 0.5 in the cell where the event is 0. In some softwares, they adjust the 0 for 0.5. It has inbuilt mechanism. Now, if there is no event in any group, then it is better to remove that study from meta-analysis. Now, in some literature, including Cochrane Handbook, it is mentioned that you can calculate risk difference based on the, even if you have 0 in both the groups, you can have that study in the meta-analysis. But then interpretation of that becomes difficult, and I always believe that things should be very simple. We should not make the things complicated so that it loses the importance. So it is better to avoid doing meta-analysis with the summary measure of risk difference. It is always better to use risk ratio or odds ratio, and if there is no event, let's remove that study from the meta-analysis. Now, rare events like 1 in 1000 or 1 in 2000 or even 1 in 100, in that context, in that situation, the meta-analysis may overestimate sometimes the results. And there are other technical issues associated with such kind of events. So the cautious approach should be used. So in your meta-analysis, if you are getting the data with rare events, then I request you to go through the Cochrane Handbook or some other literature about how to deal with such kind of data. Right now I can tell you that if the events are rare, you should be very cautious. Now another type of data which is very common is continuous. So if your data is continuous, this is the screenshot of Raman. When we click it, we will go to next in the software. Here again we have to choose one from these two. Now here we can have mainly two measures. One is mean difference and other is standardized mean difference. So here you can see here you can see that this is the first study. This is the screenshot of software Raman. So there are two groups, experimental and control. In experimental you can add mean here, standard deviation of the mean here, and total sample size. In control, mean, SD and total sample size, and you will get the mean difference here. So here you can see I have included some hypothetical data in two studies. Here mean is 45, SD is 4, sample size 50, 30, 4, 50. Next in the clinical trial 46, 3, 50, this is sample size, 36, 5 and 60 sample size. And here you can see the overall mean difference with the CI. I use fixed. This is just for the for this presentation only. I have taken the screenshot, right? And we can change it from fixed representative from here, and we can convert mean difference to standard mean difference by clicking here. So here we can see that it is very simple. You just have to add the mean and SD. So if you want to see the effect of some drug, suppose again I want to give a same example, effect of a drug on the blood pressure, systolic blood pressure, for example. And there are two groups. So in one group, experimental group, the mean after the end of the study was suppose 45. This is not good for blood pressure. Suppose it is 120, and the standard deviation of 10, and total sample size is 50. And if it's if the control, the mean blood pressure at the end of the study was 110, SD of 6 and total 50, then you will get the mean difference. So as simple as you can see here, you just have to add the data. So here you can see a forest plot with the mean difference. Now here you can see that mean difference can only be used when the measurement is done in the same scale in all the studies. So if you want to use, again I have to, if you want to use some scale for measurement of say pain, right? So in one study they have used 10 points, like 10 point VAS scale, visual analog scale for the pain. In another study, if another author has used the 100 point VAS scale for pain, this 100 and 10 cannot be combined together for the mean difference. We can have separate analysis of the studies where there is a scale of 10, and there will be separate analysis when the authors has used scale of 100, or we can use something else, and that is known as standardized difference. So when the outcome is same, but the method of measurement is different amongst the different studies. For example, as I have given an example, where the different scales are used to measure the same outcome, then we should use the standardized mean difference. So standard mean difference is basically normalized for the standard deviation of the outcome. So it's a difference in mean outcome between groups upon standard deviation outcome among participants. Now this can be used to see which intervention is better. But the problem is interpretation is difficult. Now in the mean difference we know how much is the decrease in the blood pressure, 5 mmHg or 10 mmHg. But this cannot be used, like, because this is the change in blood pressure upon SD. So that is not the real value. So interpretation is difficult, and it does not correct for the direction of the scale. If one scale is in one scale high values shows the improvement, and if in another scale low value shows the improvement, then it is difficult to combine these two studies together by using the SMD. Now this SD is also difficult to calculate, and there are different ways. In majority of cases, we have to calculate the pooled SD to measure the SMD. Though the software does it for us, but we need to understand that SD used in SMD is a little bit different than SD used in the mean difference. So both can be taken, right? Both can be taken. When this is reported, we can take this. If this is not reported, if this is reported, then also we can take this. Even we can combine these value with this value. Now the problem is, many times we want to use this value, the difference from the baseline, but many times the SD of the difference from the baseline is not available. That is the biggest hurdle. So we have the mean value of this and SD of this. We have mean value at this after 3 months, and SD of this mean value, but and we have the difference, but we don't have the SD of difference. That's why we have in those cases we have no option but to use this end of the study value. Now end of study value can be used with the difference in values, but ideally it should be used as subgroup. So we can have different subgroup for this, different subgroup of this, and as a resultant effect the difference can be shown. So it is always good to have, when we want to combine this with this value, we should put it in the form of subgroups. That will be more useful to the stakeholders. Now much better method is, but many times this analysis is not available in the published article, so there is an issue, but better to use the baseline value as covariate to adjust the result of the mean values. So the baseline value may have impact on the end of the study values. We should take end of the study value, the mean of the end of the study, but that should be adjusted mean based on the baseline values, and that should be taken into the meta-analysis. We should not pool the SMD, pool the end of the study data and the difference from baseline data in the case of SMD, because SD of the SMD is different from the MD, mean difference. Then there are various other caveats or other issues where we need to be very much cautious, and we need to understand the literature before actually conducting such kind of meta-analysis. In the case of meta-analysis of skewed data, there is a problem. So we may go for meta-analysis with the transformed data. There will be log transform data or something like that. But again, the interpretation may be difficult. Sometimes you want to combine dichotomous data with the continuous outcome. That is not a good idea, but then you have no option but to go for this kind of analysis. Then there are some methods, mathematical equations through which odds ratio can be converted into the SMDs, and vice versa also. So if you have dichotomous data in the form of odds ratio or risk ratio, which can convert into odds ratios, and if you have SMD, standardized mean difference, so you can combine these two things by converting one into another. But I would not prefer it. I would not do that meta-analysis if such kind of data is available. But if you have to do it, if it is required to do it, then this can be done. And same with the meta-analysis of ordinal data or some measurement scales, which is very, like for example, there is a measurement scale like VAS scale with 100 points that can be taken as a continuous data. But if there is this very small scale, like if there is Likert scale of patient satisfaction, 1 to 5, 5 is very much satisfied and 1 is no satisfaction. In that case, it is difficult. The meta-analysis is very difficult. So then different methods can be used. Same with the meta-analysis of counts and rates. Either you can count it into the dichotomous data or continuous data if possible, or you can take each count as the event and then it can be converted to time to event data. What to do when SD is not available? Well, this is a common problem. Many a times standard deviation is not available. In that case, we can impute standard deviations from other studies, same meta-analysis, or from studies of other meta-analysis. This all should only be done when only few studies are available. Few studies has required this imputation. If majority of studies does not have SD, then meta-analysis should not be done. As I have already highlighted in the previous slides that it is very difficult to get SD of difference in many published papers. So then there are some online calculators which use different methods, and based on that, if you add the SD of baseline and mean of baseline and sample size of baseline and SD at the end of the study, mean and sample size, then by using some method, correlational method maybe, this online calculator may count SD of difference for you. Sometimes results are given into the different subgroups and you want to use the whole group. For example, result is given for female and male, but you want to have the resultant effect of total group. Then also you can combine these groups by the formula mentioned here. All this information is available in Cochrane Handbook. In the case of time to event data, the most appropriate way is to use the survival analysis and to express the result in the form of hazard ratio. Now what hazard ratio describes? It describes how many times more or less likely a participant is to suffer the event at a particular point in the time if they receive the intervention as compared to the comparator. The best thing is to get the individual patient data from the author of the study. We should reanalyze the data, we should calculate the hazard ratio, and the hazard ratio need to be added into the software. So here you can see there are two methods through which we can do the meta-analysis of time to event data. One is O&E and variance methods. Another is generic invariance and generic inverse variance method. So here this is a screenshot. So you have to add events total from the experimental group, events total from the control group. Then we have to calculate observed minus expected effect, then variance, and then it will calculate the weight and the hazard ratio. Here they have calculated Peter-Odds ratio, right? So Peter-Odds ratio will be calculated based on the O&E, not the hazard ratio. Sorry. So here we have to calculate this O minus E upon V. That is combined together. Another method, and this requires some calculation on the part of author. So better to get the data from the original author and do this analysis and then mention data in this window. In case generic invariance, you click generic invariance here. You can use odds ratio, risk ratio as well as mean difference. So that way this is also useful if you want to have meta-analysis of the dichotomous or this kind of data, continuous data. Sometimes very useful in the case of cluster randomized trials or some other studies, quasi-experimental designs, when we have to use adjusted mean, not the actual mean. So in that case, this method is very important, because here we can use the adjusted mean. We should not use the actual mean of those conditions. Now, little bit of the heterogeneity, little bit of discussion related to heterogeneity. So heterogeneity we measures by the chi-square as well as I square, then tau, then t square. There are different methods, but Raymond calculated it by chi-square as well as the I square data. Now I square basically is the measure of the percentage of the variability in the effect size that is due to the heterogeneity rather than the sample error. So I square measures what is the contribution of the heterogeneity in the variability of the effect size. So there are different measures for some people. Less than 40% I square is not heterogeneity. For example, here there is 80%, so it will show that there is a heterogeneity. So in some reviews I have found that more than 50% is heterogeneity and less than 50% is not the significant heterogeneity. So that depends on the type of guidelines you are following. But the I score is the method which is used by Raymond and for heterogeneity, as well as there is a chi-square, which is also a method. If p-value is significant, then it means data is heterogeneous. So what to do when there is heterogeneity? Look for the data. Data may be wrong. Many times standard deviation is there, and in some study they have reported standard error. So people are, it is a very common finding where people combine SD and SEM together, so that may cause heterogeneity. Then if there is a huge heterogeneity, we may choose not to do the meta-analysis. Explore heterogeneity. We should try to explore heterogeneity. We should try to find the reason for heterogeneity. We should look into the trials. We should look into the studies. What kind of studies we are dealing with. What kind of patients were included in that studies. Where the study was done. We may choose to ignore heterogeneity if it is very less. We may perform random effect model if we presume that there may be heterogeneity. We can look into the effect measures. We may choose other effect measures. If there is heterogeneity, if there is a huge heterogeneity in relative risk, we can think of something else, some other effect measures. And if there is a studies with dubious quality, for example, a study with very less sample size or very high risk of bias, those studies can be excluded to see the effect of those studies on the heterogeneity. So, which type of assumptions we are going to follow? Fixed effect or random effect? I have already explained to you. Fixed effect is the assumptions where we believe that the true effect is same in each study, while random effect, our assumption is it is not fixed but it follows the normal distribution. It is observed that random effect model give more weightage to the smaller studies as compared to the fixed effect model. As such, smaller studies get less weightage. But if you compare these two effect models, then random effect models give more weightage to smaller studies. That is the thing which we do not want. So it is very difficult choice to use which effect of the which model for the analysis. It is better to have the analysis based on both the effects, but the choice between a fixed effect and random effect meta-analysis should not be made on the basis of statistical test for heterogeneity. For example, first you use the fixed effect model. If you found heterogeneity, then you use random effect model. This is not a right way of using the random effect model or fixed effect model. As we know that random effect gives more weightage to smaller, so we can use this decision chart which is mentioned in the Cochrane handbook, that we should calculate both. We should have first plot by both the methods, random effect models and fixed effect models. Then we can draw a funnel plot. If there is no significant asymmetry, then we can report the random effect model. So ideally we should have data for both. We should have first plot by both the random effect and fixed effect models. The question is what to report. So for that we should have a funnel plot if the studies are more than 9 or 10. And if there is no significant symmetry, because we know that random effect models give more weight to small studies. So if there is no asymmetry, means the smaller studies are equally distributed. So we can report the random effect model. If there is significant asymmetry, then we can report either both or none. It doesn't matter. We can use some sensitivity analysis by excluding the smaller studies, or we can go with meta-aggregation. So if there is a significant asymmetry, the issue is blurred. We don't know what to do. But then in the case of no asymmetry or no significant asymmetry, we should report the random effect model, the fixed one. So this was all about the data synthesis, meta-analysis part. A lot of things are there which is difficult to explain in the time given to me, but those who are interested, they can refer the Cochrane handbook to understand it better, and true knowledge will come from the actual experimentation with the software. So every time when we perform a meta-analysis, we learn something new. So thank you very much.